Mathematics is often described as the language of the universe, a bridge connecting logic and imagination. And today we embark on a journey into the heart of geometry. What you're seeing on the screen is more than a shape. It's a story of symmetry, balance, and insight. Welcome to the solution of AIME I 2024, Problem 14. The problem begins with a tetrahedron, a solid figure of four triangular faces, defined by its unique edge lengths. Let me read it for you. Let A, B, C, D be a tetrahedron such that AB equals CD equals square root of 41, AC equals BD equals square root of 80, and BC equals AD equals square root of 89. There exists a point I inside the tetrahedron, such that the distances from I to each of the faces of the tetrahedron are all equal. This distance can be written in the form m square root of n divided by p, where m, n, and p are positive integers, m and p are relatively prime, and n is not divisible by the square of any prime. Find m plus n plus p. At first glance, the problem seems complex, but if we dissect its structure, a beautiful solution emerges. We start by visualizing the tetrahedron with edge lengths derived from specific numbers. Notice how square root of 41, square root of 80, and square root of 89 can each be expressed as square root of sums of two perfect squares. This observation hints at a hidden symmetry, allowing us to embed the tetrahedron in a cuboid. Using these edges, we construct the cuboid and inscribe the tetrahedron within it. The lines you see are the edges of our tetrahedron intersecting diagonally across the cuboid faces. To solve this problem, we need to calculate two critical properties of the tetrahedron, its volume and the areas of its faces. First, let's calculate the volume of the tetrahedron. Using the dimensions of the cuboid, we determine its overall volume, subtracting the regions not occupied by the tetrahedron. Next, we compute the areas of its triangular faces, using a modified version of Heron's formula, optimized for square roots, like square root of 41, square root of 80, and square root of 89. With these values, we can determine the radius of the sphere that's tangent to all the tetrahedron's faces, also known as the inradius. This inradius connects beautifully to the problem's key formula, m square root of n divided by p. After careful computation, we find that m equals 20, n equals 21, and p equals 63. Adding them together gives us the answer m plus n plus p equals 104. The sum is 104, a result born from geometry, algebra, and a touch of ingenuity.